Hello students, today we are starting a new series, Coordination Chemistry. As a first module, we can start with an introduction to coordination compounds. These coordination compounds were not much studied till the 19th century. The reason is that the structure and bonding of coordination compounds was very puzzling or it was controversial. And it was Alfred Werner who started studies on coordination compounds, and the compounds which he started with was chloramine cobalt 3 complexes. And thus he put forward a famous theory of coordination compounds, and that was in 1823 at his age of 26. And that is why he is considered as a father of coordination chemistry. Also, he is the first inorganic chemist to get the Nobel Prize. It was in 1913. And then what are coordination compounds? Coordination compounds consist of one or more central metal ion and a number of groups or ions called ligands. So, coordination compounds contains a central metal ion and ligands bound to the central metal ion. So, the ligands are bonded to the central metal ion in the coordination compounds. Here I can give a simple example for coordination compound, that is CONH3 6 times Cl3. This coordination compound contains the central metal atom, that is cobalt, and 6 ammonia molecules are being bound to the central metal atom cobalt. And you can see a square bracket there, and outside you can see 3 chloride ions. And the complex may be charged or neutral. This complex may be charged or neutral. This is an example for a charged complex. I can give an example for a neutral complex, that is NiCO 4 times. It is an example for a neutral complex. If it is charged, it is stabilized by the counter ions. See the example CONH3 6 times Cl3. This complex, this is a central metal ion, and you have 6 ligands attached to the central metal ion. Here in this case it is ammonia molecule. And you know that the chloride ions are outside the square bracket. These are the counter ions, because this chloride ion is having a charge of -1. So, we have 3 chloride ions there, and you have the charge -3. To neutralize, you have to add the charge 3 plus in the coordination sphere. And then what is coordination sphere? It is the entity which is written in the square bracket. So, the complex part is the entity which is written in the square bracket. And this square bracket is carrying a charge of +3. And that is why for charge neutrality we are adding the counter ions, that is chloride ions. And now we have to discuss about different types of ligands. Then first of all, what are ligands? Ligands are the groups or ions directly attached to the central metal ion. They may be neutral molecules or charged molecules. They may be neutral or charged. Here you can see different examples of ligands, that is neutral ligands are there. Charged, if it is charged, it may be positive or negatively charged. Neutral ligands, for example, you can see water, H2O is a neutral ligand, NH3 molecule, it is a neutral ligand, CS, it is a neutral ligand, CO is a neutral, that is PY means pyridine, PR3 means trialkyl phosphine, EN means ethylene diamine. And coming to the negative ligands, negatively charged ligands, that is FC, F minus, Cl minus, Br minus, I minus, all these are totally we will call it as halogens. So, halogens will be the negatively charged ligands. Cyanoligand, that is Cn minus is a negatively charged ligand, SCN minus, NCS minus, NO2 minus, ONO minus, all these are carrying a charge of minus. That is why they are grouped as negatively charged ligands. And coming to the positively charged ligands, you can see that NO plus is a positively charged ligand, NO2 plus, nitrosonium, nitronium, and C7H7 plus means tropylium, and N2H5 means hydrocenium. All these are examples for positively charged ligands. So, ligands may be neutral, positively charged or a negatively charged. And likewise, we have different types of complexes also. If a complex carrying a net charge, then it is called as complex ion. See the example here, CrH2O 6 times 3 plus, the whole thing is an example for a complex ion. So, this is carrying a charge of 3 plus, that is why it is called as complex ion. And this complex ion may be positively charged, negatively charged or a neutral complex. If it is positively charged, it will certainly carry a positive charge. See, in both the cases you can see a positive, that is 3 plus charge. That is why it is grouped as positively charged complex. If it is negatively charged, you know, there it carries a charge of 3 minus. Both the example is having a charge of 3 minus. And for a neutral complexes, there will not be any charge, no positive or negative charge. So, different types of complexes are positively charged complexes, negatively charged complexes and neutral complexes. And I have already discussed about the coordination sphere, that is, coordination sphere consists of the central metal atom or ion together with the ligands, that is the whole entity which is written in the square bracket consists of the coordination sphere. The whole thing is called the coordination sphere, and usually it is enclosed in the square bracket. And the coordination number, what is coordination number? It is a number of donor atoms bonded to the central metal atom or ion in a complex. In this case, see the example of a CrH2O 6 times 3 plus. What is the coordination number of this complex? What is coordination number? It is a number of donor atoms bonded to the central metal atom. So, we have the central metal atom chromium and 6 H2O ligands are being attached to the chromium. So, how many ligands? 6 ligands. 6 ligands means H2O we have 6. So, number of donor atoms is 6. So, the coordination number here will be 6 in this example. The coordination number is the number of donor atoms bonded to the central metal atom or ion in a complex, and we have usually we have the coordination number of 4 and 6. Okay. And now another characteristic is the oxidation number. What is oxidation number? It is a charge carried by the central metal atom or ion in a complex. So, oxidation number is a charge carried by the central metal atom. For example, PtCl4 2 minus. This is an example for a complex ion. Here in this complex, that is PtCl4 2 minus, you can see 4 chloride ions are there. And you know that the chloride ions are having the charge of -1. So, in total you have -4 charge. So, -4 to become the charge -2 means -4 to become the charge -2 means what should be the charge of platinum? It should be +2. Once again I repeat, -4 for chloride ion should become -2. So, -4, how to become -2? We have to add +2. So, platinum should have the oxidation state of 2 plus. In this example, the oxidation state of platinum is 2 plus. And now, what is the charge of a complex ion? You can see the charge of the complex ion in the previous example, it is 2 plus. So, the charge of the complex ion is obtained by the algebraic sum. It is the algebraic sum of the charges carried by the central ion and the ligands coordinated to it, and thus we got the charge of the complex ion. For example, in this case, you can see chromium CrH2O 6 times 3 plus. This complex is having a charge of +3, and you have 6 ligands inside the coordination sphere. 6 ligands means 6 H2O ligands is there inside the coordination sphere, and this H2O molecule or H2O ligands are having a charge 0. So, what should be the charge of chromium? Since these molecules, 6 molecules are having the charge 0, you can say that chromium is carrying a charge of Cr3 plus. So, the whole entity, that is the complex ion, will be carrying the charge of 3 plus. And another example, that is FeCN 6 times 3 minus. In this example, you can see 6 cyano ligands are there. 6 cyano means each cyanide ligand is carrying a charge of minus 1. Okay. So, minus 1 means how many cyanide ligands are there? There are 6 cyanide ligands, that is minus 6 charge is on the total we have. And minus 6 to become 3 minus, like minus 6 to become minus 3. Then what should be the charge of ion? It should be plus 3. So, the charge of Fe should be plus 3 in this case. In here it is plus 3 oxidation state. Like that you can calculate the charge of this next complex, that is NiCO4 times. You know, CO ligand is having no charge, it is 0 charge. Again this is also having a 0 charge, and you have 4 CO ligands, and on the total you have only 0 charge. On any, you know, whether it is 2 or 3 or 4, it is not having any charge. So, the nickel is in the 0 oxidation state because there is no charge outside. So, nickel is having the 0 oxidation state, and what is the charge of this complex part? It is also 0, and that in this way you can calculate the charge of the complex ion, oxidation state of the central metal atom. Okay. And now we have different types of ligands. It is based on the denticity of ligands. And then what is denticity? Denticity is the number of donor atoms with lone pair electrons in a ligand that can form bond with the central metal atom. That is called denticity. So, what is denticity? It is a number of donor atoms which are giving electrons to the central metal atom while forming a coordination complex. And based on the denticity, ligands are classified into different types. Firstly, you can see that first classification is that is a unidentate ligand, or it is monodentate. It is also called as monodentate ligand. Means mono or uni means 1. So, the number of donor atom that can form bond with metal is 1. So, unidentate ligand 1. The donor atom is 1. And examples for monodentate ligand or unidentate ligands are halogens generally, that is Cl minus, Br minus, I minus, etc. are example for a unidentate ligand because the donor atom is only 1. And also you have H2O ligands, water, it is also an example for a unidentate ligand. Ammonia molecules are a unidentate ligand. Cyano ligands are also unidentate ligand. In all these cases you have the donor atom 1. Okay. And now the second class generally we will classify as polydentate ligand. Poly means more than 1. So, more than 1 donor atoms are bonded to the central metal ion in the polydentate ligand. And this polydentate ligand are also further divided into bidentate, tridentate, tetradentate, hexadentate, etc. Poly means many. If it is bidentate, you know, bi means 2. So, in bidentate ligand that we have 2 donor atoms, and the examples are En means ethylene diamine. Ethylene diamine ligand is an example for a bidentate ligand. Oxalato ligand, it is also a bidentate ligand. In both the cases you have the 2 donor atoms. And the second class is tridentate ligand. Tri means 3. So, they will be having 3 donor atoms. Example is diene, diethylene triamine. And you have tetradentate ligand. Tetradentate ligand contains, or they consist of 4 donor atoms. So, these 4 donor atoms will be bonded to the central metal atom. An example is triene, triethylene tetraamine. They are having 4 donor atoms. And finally, you have hexadentate ligand. Hexa means 6. So, they will be containing 6 donor atoms, and the example for such a ligand is EDTA, or it is ethylene diamine tetraacetic acid. Ethylene diamine tetraacetic acid. They will be, this ligand is having 4 oxygen atoms and 2 nitrogen atoms. So, 4 plus 2 we have 6. On total you have 6 donor atoms in the case of ethylene diamine tetraacetic acid. So, these are the different types of ligands, and you have another type of ligand, that is ampidentate ligand. Ampidentate ligands means they contains two different donor atoms, but at a time one will be bonded to the central metal atom. So, ampidentate ligands are having two donor atoms, at a time one will be bonded. Okay. And the examples are SCN minus, NO2 minus, etc. In the case of SCN minus, this sulfur is bonded to the central metal atom, and in the case of NCN minus, it is nitrogen bonded to the central metal atom. SCN minus and NCN minus. The only difference is through which atom it is being attached to the central metal. Okay. And in the case of NO2 minus, it is nitrogen that forms bond with the central metal atom. In the case of ONO minus, it is oxygen. By convention, we use NO2, we'll call it as nitro ligands, and ONO as nitrito, nitro and nitrito. And the next class of ligands is bridging ligands. In the bridging ligands, they can simultaneously bind to the two metal atoms at a time. This is an example for a bridged complex. In this complex, you have two ligands that forms bridge with this two metal ions. The example in this case, the metal ions are same, that is cobalt, and here also it is cobalt. But this OH, hydroxo ligand, is forming a bridge between these two cobalt atoms. That is why it is called a bridging ligand. Okay. And so, you have different types of ligands based on the denticity. You have different types, that is denticity means it is the number of donor atoms that forms the bond with the central metal atom, and based on denticity you have different classes, monodentate or it is called unidentate, means donor atom is one, and second class is polydentate ligand. Generally poly means many, more than one, that is more than one donor atoms are there in polydentate ligand. The polydentate ligands are further classified as bidentate, tridentate, tetra, hexa, etc. based on the number of donor atoms, and you have different examples for that. And you have another class, that is ampidentate. They are having two donor atoms, but at a time only a single donor atom is forming bond with the central metal atom. Examples are given. And finally, it is bridging ligands. Bridging ligands means they will simultaneously bind to the two metal atoms at a time. And now, these are the ligands and their charges. This part is very important in coordination chemistry, because one should understand what is the charge of each ligand. To calculate the oxidation state of the central metal atom, coordination number, etc. should be understood clearly in the coordination chemistry. So, this part is very important. First ligand is ammonia ligand. Ammonia ligand is given by the symbol NH3, and the name is amine. Okay, and they will be having the charge carried by the ammonia ligands is 0. And next is water, H2O. It is named as aqua, and the charge is 0. Next is CO, carbonyl ligand. Again it is named as carbonyl. Carbon monoxide, CO is carbon monoxide, but the name is carbonyl. The charge carried by this ligand is also 0. And now coming to the next type, that is OH minus, it is hydroxo ligand. It is having a charge of -1. Now we have F minus, Cl minus, Br minus. All these are halogens. Totally I can say these three are halogens. Fluoro, chloro, bromo. All these are having the charge of -1. And now you have NO. NO ligand is a nitrosyl ligand. It is also a chargeless because it is having 0 charge. And next is NO plus. It is named as nitrosonium. That is, it is having a charge of +1. That is to be noted. That is, we have a positively charged ligand. That is NO plus. And now we have H minus. H minus is named as hydrido, and it is also having a charge of -1. Next is cyano, Cn minus. Cyano is having the charge of -1. NO2 minus, or it is nitro. You can call it as nitro, or it is it can be named as nitrito N, which shows that the donor atom is nitrogen in this case. To show that donor atom is nitrogen, we can write as nitrito N, or you can call as nitro. The charge is -1. And SCN minus, it is also called as thiocyanito, that is having a charge of -1. EN is ethylene diamine, it is having a charge 0. OX is oxalato ligand, it is having a charge of -2. And DMG means dimethyl glyoxamato ligand, it is having a charge of -1, and ethylene diamine tetraacetic acid having a charge of -4. And these are the charge carried by the different ligands. And now you can calculate the oxidation number and coordination number of different complexes. This is very important. You have to, as an introduction to coordination chemistry, this is the first thing should be studied. So, first example is NiCl4 2 minus, the central metal atom nickel, Ni. And how many ligands are there? You have 4 chloride ligands. Chloride ligands is having a charge of -1. So, what is the charge carried by, in the total, how many charges carried by the ligands? It is -4. So, -4 to become -2 means nickel should have the oxidation state. See, -4 to become -2. -4 for chloride to become -2 means nickel should have the oxidation state of, it should have the oxidation state of +2. Okay. So, Ni will be having the oxidation state 2+. So, that is all about the oxidation state. And now we can calculate the coordination number. What is the coordination number? Coordination number is a number of donor atoms that are attached to the central metal atom. In the case of NiCl4 2 minus, which is a ligand that is attached to the nickel, it is chloride ions, and chloride ions are unidentate or a monodentate ligand. So, one donor atom is there. How many chloride ions are there? 4 chloride ions. So, the coordination number in this case is 4. Okay. So, oxidation state is 2+, and coordination number is 4. Second example is K4FeCN6. See this example. You can see that 4 K plus ions. You know that potassium is having a charge of +1. So, how many potassium ions are there? 4 potassium. 4 plus will be given from potassium in this case. To neutralize that, the whole entity, that is the coordination, the complex ion should carry the charge of -4. 4 minus charge should be given to the coordination sphere. And now, what are the ligands attached? What type of ligand is that? That is cyanide ligand, cyano. Cyano ligands are having a charge of -1. They are unidentate or monodentate ligand. So, how many cyano ligands are there? It is 6 cyano ligands. 6 cyano ligands, that is each will be carrying a charge of -1. On total you have -6 charge for the ligands. And -6 to become -4. -6 to become -4 means this iron, that is Fe, should carry the charge of +2. So, iron will be having the charge of 2+. And we have calculated the oxidation number in the second complex, it is 2+. Now, coming to the coordination number. What is coordination number? It is the number of the donor atoms that is attached to the central metal atom. In this central metal atom is iron. How many ligands are there? 6 cyano ligands are there. Cyano ligands are unidentate ligand. So, there will be 6 donor atoms, and the coordination number here should be 6. Okay. So, that is all about the second complex. Now, coming third complex, MnH2O 6 times Cl3. In this example, you can see firstly you have to calculate the oxidation state of manganese. Manganese is a central metal atom. To calculate the oxidation state, firstly you have to consider there are counter ions, 3 chloride ions are there. So, on the whole you have -3 charge for the 3 chloride ions. To neutralize, you should give 3+ to the coordination sphere, 3+. And you know that H2O ligands are having the charge of 0. 0 charge is given for the H2O ligands, and so this 3 plus will be for manganese, right. Again I repeat, you can see that 3 chloride ions are there, 3 minus will be there for chloride ions. To stabilize, you should give the 3 plus charge to the whole coordination sphere, and you know that H2O ligands are having 0 charge, and that is why manganese is in the plus 3 oxidation state. And you can see the fourth example, that is C2O4 twice 2 minus, and the complex is having the central metal atom copper, and we can calculate the oxidation number. You know that the charge on the complex is 2 minus, and the ligand is oxalato ligand. Oxalato ligand is having a charge of minus 2, and how many oxalato ligands are there? 2 oxalato ligands. So 2 charge for 2 oxalato ligands. So on the total you have minus 4 charge for the ligands, and minus 4 to become minus 2. Minus 4 to become minus 2 means what should be the oxidation state of copper? It should be plus 2 oxidation state. So copper is here having a plus 2 oxidation state, Cu2 plus. And now we can calculate the coordination number of the complex. Coordination number of the complex is oxalato ligand is a bidentate ligand. So bidentate means you have 2 donor atoms. 2 donor atoms are there for 1 ligand. And how many ligands are there? You have 2 ligands. So on the total, what should be the coordination number? It is 1 oxalato ligand is having 2 donor atoms. How many oxalato ligands? 2. On the whole you have 4. Here the coordination number is 4 in this complex. Okay. And now different other examples are also there. Na3FeCN 6 times. This complex is having the counter ion as sodium. Sodium ions will be forming plus 1, right. So how many sodium ions are there? 3 plus. 3 plus should be given here. For the stability, we have to give 3 minus to the coordination sphere. Again I repeat. So how many sodium ions are there? 3 sodium ions are there. Each sodium ion is having a charge of plus 1. So the plus 1 into 3 means plus 3. Plus 3 for neutralizing, you have to add 3 minus to the coordination sphere. And now looking to the coordination sphere, how many ligands are there? 6 ligands. What type of ligands is given there? It is cyano ligands with a charge of minus 1. How many cyano ligands? 6 cyano ligands. So on total you have minus 6 charge for the cyano ligand, and minus 6 to become minus 3. Minus 6 to become minus 3. What should be the charge of iron? It should be plus 3. Plus 3. So Fe is in the plus 3 oxidation state. So we have calculated the oxidation number of this complex, that is plus 3. And now we can calculate the coordination number. Again, cyano ligand is a monodentate or unidentate ligand. Number of donor atom is 1. How many donor atoms will be there? There is 6. So, coordination number is 6. And now another example. It is PtH2O 4 times. PtH2O 4 times. In this complex, you have the central metal atom platinum. H2O is a neutral ligand, that is charge 0. So that charge is 0. Again, platinum will be in the 0 oxidation state. So oxidation number of the central metal atom will be 0 here. No charge is given outside the coordination sphere. So the platinum is 0. And now what is the coordination number? Coordination number is 4 because H2O is a unidentate ligand, 4 ligands are there. So the coordination number here is, it is 4. And now another example, CONH3 6 times 3 plus. Again the central metal atom is cobalt, and you can see the charge of plus 3 outside. plus 3 outside, how many ammonia ligands? 6 ammonia ligands, but ammonia ligands are carrying a charge of 0, it is 0. So, the cobalt should carry the charge of CO3 plus, because ammonia ligands are having 0 charge. And we have calculated the oxidation number, that is 3 plus. And now coordination number, again it is coordination number is 6. Why? Because this ammonia ligands are monodentate ligands. So, we can just give the number of ligands. And now finally, you have final example is CrH2O thrice Cn thrice plus. The central metal atom is chromium, and you have given the charge of +1 outside the coordination sphere. Again, to calculate the oxidation number of the central metal atom, cyano-ligands means there are 3 cyano-ligands, each cyanoid ligand or cyano-ligand is carrying a charge of -1. So, -3 will be there because 3 cyano-ligands are there. H2O is having a charge of 0. So, -3 to become +1, -3 to become +1. What should be the oxidation state of chromium? It should be +4. Okay. So, chromium is 4 plus oxidation number. And to calculate the coordination number, again you can count the number of ligands. Both the ligands are unidentate or monodentate ligand. So, you can just add the number of ligands here. We have 3 H2O molecules or H2O ligands plus 3 cyano ligands. So, 3 plus 3, that is 6. Coordination number is 6 in this complex. In this class, we have discussed about coordination compounds, some introduction for coordination compounds, what is a central metal atom, what are ligands, what are the different types of ligands, how can we calculate the oxidation state, coordination number, etc., what are the charges for different ligands, etc. And you have studied how to calculate the coordination number of a complex ion and the oxidation state of the complex ion, etc. And in the next class, we will be discussing about the nomenclature of coordination compounds. How can we name? There are certain rules for naming this coordination compounds. That will be discussed in the next class. Thank you for watching this session. Thank you.